Hello everyone. In this session, we are going to see about the theoretical part of Unit 4 Deflection of Beams in the paper Strength of Materials for Mechanical Engineers. So first, general theory. When a beam bends, it takes up various shapes such as that illustrated in figure. The shape may be superimposed on XY graph with the origin at the left end of the beam before it is loaded. At any distance x meters from the left end, the beam will have deflection y and a gradient or slope dy by dx, and it is this that we are concerned with in this tutorial. That is, the image is given in the next slide. So from that image you can able to understand this concept. So uh, these relations are obtained from even beam theory and also in engineering mechanics, that m by I is equal to E by R. That is, m is nothing but the bending moment and I is the second moment of area about the centroid, which is obtained from the engineering mechanics third unit, and E is the modulus of elasticity and R is the radius of curvature. So in this diagram we can able to found that it is a beam, that is, this is a beam, right? And on applying a load between these 2 points A and B, so on the application of load, the beam can become like this. Hence, this will be the del x is the distance between A and B, that is the length on which load is applied. That will become del S. Del S is nothing but slope, right? So sigma by y is equal to m by I is equal to E by R is the engineering beam theory. We had already known this from the first year itself, that is engineering mechanics paper itself. So if the deformation is small, that is del s is small, that is there will not be any y, that is deflection, hence ds becomes dx, that is a flat one. So from the previous image, that applied load between the point AB, that is taken seriously. So from this diagram we can found that this R is nothing but the radius of curvature by application of load, and A B become A dash and B dash. Since it gets deflected, the dimension gets changed and it gets a curvature shape from the flat surface. So the curvature shows that there will be angles, right? And the angle from the radius of curvature is represented as d theta at x direction, and at y it will be termed as dy, that is del y. This will be the deflection, right? And ds is the distance between, that is modified distance between the point A and B, right? Hence from this it looks like a curve, it looks like a curve. So from this curve we can able to get the slope, right? So on getting a triangle from this slope, I think you hope understand from this laser pointer, right? So r d theta is equal to ds, which is equal to dx. Since if the slope is very small, ds is equal to dx, and d theta is nothing but the dy by dx, that is the slope, the relation to find the slope. Hence 1 by r becomes d square y by dx square, right? Since d theta is equal to dy by dx, so d, that is differential of dy by dx, is equal to d square y by dx square. This can be alternatively obtained from this Newton's curvature equation. R will be the radius of curvature. On plotting this curve in xy graph, that is y is equal to function of x, that is f of x. 1 by r is equal to d square y by dx square by 1 plus dy by dx whole square whole power 3 by 2. If the value of dy by dx square is very small, then it will becomes 1, and hence 1 by r is equal to d square y by dx square. And how this 1 by r is equal to m by I is obtained is given in this diagram. Consider this as a curve, and this will be the starting point x, and this will be the y, that is this point will be the origin, and hence this is the radius of curvature on this curve. So it gets a tangent line, right? Hence this will be the r, that is radius of curvature. And mathematically it can be shown that any curve plotted on XY graph has a radius of curvature. So whatever the curve is, if this curve is not like this, and consider that a sinusoidal curve, that curve also have a radius of curvature, and it can be represented in this relation: 1 by r is equal to d square y by dx square plus 1 by dy by dx whole power 3 by 2, right? If this dy by dx whole power 3 by 2 value will be very small, that is like this, similar to a straight line but a little bit bend one, that is a spline line, then it becomes 1, and so 1 by r becomes d square y by dx square. And so m bending moment will become ei d square y by dx square. So m is the bending moment and ei is the flexural stiffness and d square y by dx square is the curvature, right? These are all the parameters from this engineering beam theory. So what are the relationship between this slope, deflection, shearing force, etc.? So consider this is a beam AB with a point load at a point C. Hence, on application of a point load, this beam will become like this, right? This change in dimension in y direction is termed as deflection, that is y, right? And slope is nothing but dy by dx. So that is the rate of change of deflection in terms of x distance. So consider this will be the x direction, this will be the y direction, and when we are plotting this deflection based on the distance, we will be getting a curve that is termed as the slope dy by dx, and bending moment, that is m is equal to ei d square y by dx square. This is the curvature, ei is the flexural stiffness, and m bending moment. This relation is obtained from the previous slide, and on differentiating this equation we will get shearing force, that is ei d cube y by dx cube. On again differentiating we will get rate of loading, ei d power 4 y by dx power 4. So this is the relation between these parameters, that is applying the load will get the beam gets deflection, that is on plotting the graph in xy, that is the rate of change of deflection in terms of x distance, we will be getting slope, and from the slope the differentiation we will get ei d square y by dx square. So this relation is represented in the previous slide. M is equal to ei d square y by dx square. This d square y by dx square is termed as the radius of curvature, and ei is the flexural stiffness, right? On differentiating this bending moment we will get shearing force, and on again differentiating we will get rate of loading. So this is the relation. And what are all the methods available to find this slope and deflection of a beam? The beam can be whatever, either cantilever, simply supported, overhanging, whatever the beam, and also the load is point load, UDL, UVL, that is uniformly distributing load, uniformly varying load, whatever. How to find the slope and deflection of a particular beam with the given loads? Double integration method, moment area method, Macaulay's method, and conjugate beam method. So in this session we will see about this double integration method in detail. That is d square y by dx square is equal to m by ei. That m is taken out and 1 by e is represented here. So this is the relation gives the curvature. On integrating this curvature we will get the slope, that is integral of d square y by dx square will become dy by dx, and 1 by ei is the constant one, and integral of m become m dx plus c1 is a constant. So integrating the curvature relation we will get a slope, and integrating again the slope equation we will get the deflection, that is y is equal to 1 by ei double integral of m dx, that is integral of m dx will become double integral of m dx into dx plus c1 dx plus c2 is the second constant on integrating the slope equation, which provides the deflection of a particular beam. So by this double integration method, the slope and deflection to find the beam, that is slope and deflection of a beam, particular beam given, right? So the curvature c1 and c2 are the constant, that is the boundary conditions, and curvature is represented in R, and the slope is the, as I said already, that is the rate of change of deflection in terms of the distance x. Dy by dx will be the slope, and the deflection is nothing but the maximum curve obtained due to the applied load. So by this method, double integration method, the slope and deflection to find simply supported beam with a point load and then uniformly distributed load in the beam, right? So this is a simply supported beam, which means at its two ends there will be a support with a point load at its center. Then the slope to find is dy by dx. Theta a is equal to theta b, which is equal to minus wl square by 16ea. Since theta a and theta b is nothing but the deflection at point A, deflection at point B will be equal. Since at point A there will not be any deflection, at point B there will not be any deflection. The deflection will be at the point where the load is applied, right? And hence theta A is equal to theta B is equal to minus wl square by 16ea. This is obtained from the derivation. And also the deflection yc is equal to minus wl cube by 48 ei. And also the slope and deflection for uniformly distributed load. So since it is a uniformly distributed load, we have to take a particular point x. We should consider a particular point either at this point, at this point, at this point, whatever. We have to consider a point and we should take as the distance x, and on derivating this uniformly distributed load on a beam, we will get slope and deflection, that is theta a theta b, that dy by dx equal to minus wl square by 24 ei, and deflection yc is equal to minus 5 by 84 wl cube by ei. So these are the formulas to find the slope and deflection of a given beam with a given type of loads. So with this I conclude the session. In this session we will see about the problems and also the expressions. Thank you.